All right, so this is CS50, and this is the end of week 4. And one of the topics today is that of digital forensics, the art of recovering information. And indeed, even though you're in the midst right now of PSET 3 and Breakout, next week the focus will be on precisely this domain. So one of the coolest jobs I ever had was back in graduate school when I was working for the local Middlesex County District Attorney's Office doing forensics work. So essentially the Massachusetts State Police, on occasion, when working on cases, would bring in things like hard drives and floppy disks and memory cards and the like, and they would hand them to me and my mentor, and our goal was to find evidence, if there was any, on these media. Now, you might have seen glimpses of this world of forensics in the media, TV and movies, but the job I had, and dare say that world, is not quite like you would see. Let's take a look at what you've probably seen.
Okay. Now let's get a good look at you.
Hold it. Run that back.
Wait a minute. Go right.
There, freeze that.
Full screen.
Okay, freeze that.
Tighten up on that way.
Vector in on that guy by the back wheel.
Zoom in right here on this spot.
With the right equipment, the image could be enlarged and sharpened.
What's that?
It's an enhancement program.
Can you clear that up any?
I don't know. Let's enhance it.
Enhance section A6.
I enhanced the detail, and
I think there's enough to enhance. Release it to my screen.
Enhance the reflection in her eye.
Let's run this through video enhancement.
Edgar, can you enhance this?
Hang on. I've been working on this reflection.
Someone's reflection.
the reflection.
There's a reflection of the man's face.
The reflection.
There's a reflection.
Zoom in on the mirror.
You can see a reflection.
Can you enhance the image from here?
Can you enhance him right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance.
Zoom in on the door.
Times 10.
Zoom.
Move in. More.
Wait, stop.
Stop.
Pause it.
Rotate us 75 degrees around the vertical, please.
Stop. Go back to the part about the door again.
Got an image enhancer that can bitmap?
Maybe we can use the Predict Send method to see into the windows.
This software is state-of-the-art.
The eigenvalue is off. With the right combination of algorithms.
He's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
Enhanced.
Enhance.
Freeze and enhance.
So those were all words, but they were not used in sentences correctly. And indeed, in the future, anytime, please, you hear someone say the word enhance, chuckle just a little bit. Because when you try to enhance, for instance, this is what happens. So here's a gorgeous photo of CS50's own Davin. And suppose that we wanted to focus in on the twinkle in his eye or the reflection of the bad guy that was clearly captured by the security camera. This is what happens when you zoom in on an image that has only a finite number of bits associated with it. That is what you would get. And indeed, in Davin's eye is but 4, maybe 6 pixels that compose exactly what was glimmering there. So problem set 4 will ultimately have you explore this world, particularly by nature of something we'd call file I/O, where I/O is just a fancy way of saying input and output. So thus far, all of the interactions we've had with a computer have been largely with your keyboard and the screen, but not so much with the hard disk or saving of files beyond the ones you yourself write. Your programs thus far have not been creating and saving and updating their own files. Well, what's a file? Well, something like a JPEG. This is an image you might have or upload to Facebook or see anywhere on the web. Indeed, that photo we just saw of Davin was a JPEG. And what's interesting about files like JPEGs is that they can be identified, typically, by certain patterns of bits. In other words, what is it that distinguishes a JPEG from a GIF, from a PNG, from a Word document, from an Excel file? Well, it's just different patterns of bits, and those different patterns are usually at the start of those files. So that when a computer opens a Word doc, or when a computer opens a JPEG, it looks typically at the first several bits in the file, and if it recognizes a pattern, it says, oh, this is an image, let me display it to the user as a graphic. Or, oh, this looks like a Word doc, let me show it to the user as an essay. So for instance, JPEGs, it turns out, are fairly sophisticated underneath the hood, but the first 3 bytes in most every JPEG start with these 3 numbers. So byte 0, 1, and 2 are in most every JPEG 255, then the number 216, then the number 255. And what you'll be able to start doing next week is actually poking underneath the hood of files like JPEGs and like bitmap files and seeing what's always been there for as long as you've been using a computer. But what's there is not typically written like decimal numbers like this. Computer scientists don't tend to speak in decimal. They don't really speak in binary. Typically, when we want to express numbers, we actually use hexadecimal, which you may recall from, say, problem set 1, which challenged you to think about a different system. We, of course, are familiar with decimal, 0 through 9. We talked about binary, and we don't really have to use that much here on out, because computers will use that. But programmers will very often, but not always, use hexadecimal, which just means you have 16 letters in your alphabet, as opposed to 2 or 10. So how do you count to higher than 9 in hexadecimal? You go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F, just by convention. But what's key is that each of these is a single symbol. There is no 10, there is no 11 per se, because each of your digits, just like in decimal and just like in binary, should just be a single character by convention. So that then is the alphabet we have at our disposal for hexadecimal. So what does a JPEG look like if you were to write out those first 3 bytes, not as decimal, but for instance as hexadecimal? And why is hex even all that useful? Well, a quick look at an example. So if I write out the bits that represent these decimal numbers. And this might be a little rusty now from a few weeks back, but the left one and the right one are pretty easy, right? 255 was the biggest number we could represent with 8 bits. It was all ones. So the only one that's mildly interesting is the middle one, and if you kind of do out the math, you will deduce that indeed that pattern of 1 and zeros represents 216. So let's just stipulate for now that these are correct. But why is this interesting? Well, a byte, of course, is 8 bits, and it turns out that if you think of a byte as 2 chunks of 4 bits, like this, let me just add some space. So before, after, I've just added some white space for visualization's sake here. How might we now represent, in say hexadecimal, each quad of bits, each set of 4 bits? So for instance, on the left now we have 1, 1, 1, 1 in binary. What is that number in decimal? If you do out the math, you have the 1's place, the 2's place, the 4's place, and the 8's place. It's 15. So if we do 8 plus 4 plus 2 plus 1, we get 15. So I could write down 15 below 1, 1, 1, 1, but the whole point here is hexadecimal, not decimal. So instead of writing down 15, 1, 5, I'm going to write that in hex, which, if you think back, if you have 0 through F, what is 15 going to be? So it turns out it's F. And you can work that out by saying, well, if A is 10, then, OK, F is 15. So indeed, we could rewrite this same set of numbers as FF. And then if we do a bit of math, we'll deduce that that's D. 8 is pretty easy, because we have a 1 in the 8's place. And then we have a couple of more FFs. So what humans tend to do by convention when they use hexadecimal is they just write this a little more succinctly, get rid of most of that white space. And just to be super clear to readers that this is hexadecimal, the simple convention among humans is you write 0x, which has no meaning other than a visual identifier of here comes a hex number. And then you put the 2 digits, FF in this case, then D8, then FF. So long story short, hexadecimal just tends to be useful because each of its digits, 0 through F, perfectly lines up with a pattern of 4 bits. So if you have 2 hexadecimal digits, 0 through F, again and again, that gives you perfectly 8 bits or 1 byte. So that's why it tends to be conventionally useful. There's no intellectual content really beyond that other than its actual utility. Now, JPEGs aren't the only file formats for graphics. You might recall that there are files like this in the world, at least from a few years back. So this was actually installed in Windows XP on millions of PCs around the world, and this was a bitmap file, BMP. And a bitmap file, as you'll see next week, just means a pattern of dots, pixels as they're called, a map of bits, really. So what's interesting, though, about this file format, BMP, is that underneath the hood, it has more than just 3 bytes that compose its header, so to speak, the first few bytes. It actually looks a little complicated at first glance. And you'll see this in the pset, and getting something particular out of this now isn't so important as just the fact that at the beginning of every bitmap file, a graphical format, there's a whole bunch of numbers. Now, Microsoft, the author of this format, tends to call those things not ints and chars and floats, but words and dwords and longs and bytes. So they're just different data types or different names for the same things. But you'll see that in pset 4. But this is only to say that if a human double-clicks some .bmp file on his or her hard drive and a window opens up showing him or her that image, that happened because the operating system presumably noticed not only the .bmp file extension in the file name, but also the fact that there's some convention to the pattern of bits at the very beginning of that bitmap file. But let's now focus not on such a complicated file, but instead on something like this. Suppose here, in gedit, I just have the beginnings of a program that's pretty simple. I've got some includes up top. Now I've got include structs.h, but I'll come back to that in a moment. But this is useful for now. So this is a program that's going to implement like the registrar's database, so a database of students. And every student in the world has like a name and a house and probably some other stuff, but we'll keep it simple. Every student has a name and a house. So if I wanted to write a program whose purpose in life was just to iterate from 0 on up to 3, there's 3 students at Harvard University, and I just want to get, using getString, each student's name and house, and then just print those out. This is sort of like week 1, week 2 stuff now, where I just want a for loop or something like that, and I want to call getString a few times, and then printf a few times. So how might I do this, though, when both a name and a house are involved for each student? So my first instinct might be to do something like this. I might first say, well, give me, say, an array of strings called names, and I don't want to hard code 3 here. What do I want to put there? So students, because that's just a constant declared at the top, just so I don't have to hard code 3 in multiple places. This way I can change it one place, and it affects a change everywhere. And then I might do string houses, students. And now I might do something like for int I get 0, I is less than students, I plus plus. So I'm typing fast, but this is probably familiar syntax now. And now, this was more recent. If I want to put in the ith student's name, I think I do this. And then, not names, but houses, bracket I do this, get string. And let me go back and fix this line. Agree? Disagree? It's not very user-friendly. I haven't told the user what to do. But now, if I also wanted to later, let's say, print these things out, so to do later, I'm going to do more with this. This arguably is a correct implementation of getting names and houses, 3 of them total of each, from a user. But this is not very good design, right? What if a student has not just a name and a house, but also an ID number, and a telephone number, and an email address, and maybe a home page, and maybe a Twitter handle, and any number of other details associated with a student or a person more generally? How would we begin to add functionality to this program? Well, I feel like the simplest way might be to do something like, let's say, int IDs students, so I can put all their IDs in there. And then for something like phone numbers, I'm not sure how to represent that just yet, so let's go ahead and just call this Twitter's students, which is a little strange, and a bunch more fields. I've started to effectively copy and paste here. And this is kind of going to grow pretty unwieldy pretty quickly, right? Wouldn't it be nice if there were in the world a data structure known not as an int or a string, but something higher level, an abstraction, so to speak, known as a student? C did not come with built-in functionality for students, but what if I wanted to give it such? Well, it turns out, I'm going to open a file called structs.h here, and you can do exactly that. And we're going to start doing this now. And underneath the hood of pset3, you've already been doing this now. There is no such thing as a grect or a goval in the programming language C. Folks at Stanford implemented those data types by using this approach here, declaring their own new data types using a new keyword called struct and another one called typedef. And indeed, even though this syntax looks a little different from stuff we've seen before, in principle, it's super simple. This just means define a type that's going to be a structure, and a structure is just like a container for multiple things, and that structure is going to have a string called name and a string called house, and let's call, just for convenience, this whole data structure student. So the moment you get to the semicolon, you have now created your own data type called student that now stands alongside int and float and char and string and grect and goval and any number of other things people have invented. So what's useful about this now is that if I go back to struct 0 and finish this implementation, which I wrote in advance here, notice that all of the inevitable messiness that was about to start happening as I added phone numbers and Twitters and all these other things to a student's definition, now it's succinctly wrapped up as just one array of students. And each of those students now has multiple things inside of it. So that just leaves one question. How do you get at the name and the house and the ID and whatever else is inside of the student? Super simple as well. New syntax, but a simple idea. You simply index into the array, as we did last week and this. And what's clearly the new piece of syntax? Just dot, which means go inside the structure and get the field called name, get the field called house, get the field called student. So in pset3, if you're still working on that, and most folks still are, realize that as you start using things like grecs and govals and other things that don't seem to have come from week 0, 1, or 2, realize that just because Stanford declared some new data types, and indeed that's exactly what we'll do as well in pset4 when we start to deal with things like images, bitmaps, and more. So that's just a teaser and a mental model for what is to come. Now, I procrastinated a bit this morning. I was kind of curious to see what the Microsoft wallpaper actually looks like today. And it turns out someone in 2006, I think, actually went to almost precisely the same spot to photograph, in reality, what looks like that these days. The field is now a little overgrown. So speaking now of images, let's bring back Davin here on the screen and Nicholas, and just remind you that if you'd like to join us for lunch this Friday, head to our usual URL here. So where did we leave off on Monday? We introduced this problem, right? This was seemingly a correct implementation of swap, whereby you take in two ints, one called A, one called B, swap them, just like Laura did here on stage with the milk and the water, by using a temporary variable or an empty cup so that we could put B in A and A in B without making a mess of things. We used a variable called temp. But what was the fundamental problem with this code on Monday? What was the problem here? Yeah. Takes up more space because I'm using a variable, and that's OK. That is true, but I'm going to say that's OK. It's only 32 bits in the grand scheme of things, so not a big deal. Other thoughts? Exactly. It only swaps the variables locally, because anytime you call a function, when I had the trays from Annenberg last time, you have main on the bottom. As soon as you call a function called swap, swap does not get x and y, the original values. What does swap get, did we claim? So copies of them. So it gets 1 and 2, if you recall the example from last time, but a copy of 1 and 2 that are successfully swapped, but unfortunately in the end, those values are still the same. So we can see this with our new friend, hopefully GDB, that you or the TFs and CAs have been guiding you toward as follows. So no swap, recall, looks like, let's open up this, looks like this. We initialized x to 1, y to 2, had a bunch of printfs, but then the key call here was to swap, which is exactly the code we just saw a moment ago, which is correct at first glance, but functionally this program does not work because it doesn't permanently swap x and y. So let's see this. A quick warm-up here with GDB, a /no swap, a bunch of overwhelming information that I'll get rid of with Control-L for now. And now I'm going to go ahead and run it. And unfortunately, that was not that useful. It ran the program inside of this program called GDB, a debugger, but it didn't let me poke around. So how can I actually pause execution inside this program? So break, and I could break on any line number, 1, 10, 15, but I can also break symbolically by saying break main, and that's going to set a breakpoint apparently at line 16 in main. And where is line 16? Let's go up to the code and go up to no swap, and indeed, line 16 is the very first in the program. So now, if I go ahead and type run this time, enter, it paused. So let's poke around. Print x. Why is x 0? And ignore the $sign. That's just for fancier usage of the program. Why is x 0 at the moment? Yeah.
It paused right before line 16. You haven't actually run line 16.
Exactly. GDB by default has paused execution just before line 16, so it hasn't executed, which means x is of some unknown value, and we got lucky that it's something clean like 0. So now if I type next, now it executed 16. It's waiting for me to execute 17. Let me go ahead and print x. It's 1. Let me go ahead and print y. What should I see now? A little louder? Okay, not quite consensus. So yes, we see some garbage value. Now, why is 134514064 there? Well, it's just some garbage value. My program uses RAM for different purposes. There's other functions other people wrote inside of my computer. So those bits have been used for other values. And what I'm seeing is like the remnants of some prior use of that memory. So no big deal, because as soon as I type next and then print y, it's initialized to the value that I want. So now let's go ahead a little faster. N for next. Let's do it again. Let's do it again. But I don't want to hit it here, because if I want to see what's going on inside of swap, what's the command? Step. So this steps me into a function rather than over it. And now it's a little cryptic, honestly, but this is just telling me I'm in line 33 now. And let's do this again. Print temp, garbage value, negative this time, but that's just still a garbage value. So let's do next. Print temp. It's initialized to 1. Which was the value of x, aka a. Now, where are a and x coming from? Well, notice in main, we called these values x and y. We then passed them to swap as follows. X came first, comma, y. And then swap could call them x and y, but for clarity, it's calling them a and b. But a and b are now going to be copies of x and y, respectively. So if I go back to DB, temp is now 1, and a is now 1. But if I do next, and now do print a, A has already been moved over. The milk has been poured into the former orange juice's glass, or vice versa. And if I do next again, and now if I print out as a sanity check, A is still 2, but B is now 1, frankly, it's still there. I don't care what temp is. But as soon as I now type, let's say, continue, to go back, now I'm at the end of the program, and unfortunately, X is still 1, and Y is still 2. So what was the utility of GDB there? It didn't help me fix the problem per se, but it hopefully helped me understand it by realizing that, yes, my logic is right, but my code is not ultimately having a permanent impact. So that's a problem we're going to now solve today. But let's get there by way of this. String is a lie. It, too, is not a data type that exists in C. It's been a synonym for some time for something else, and we can reveal that as follows. Let me go ahead and open up a program called compare 0. And rather than type this one out, we'll start to walk through the code I already wrote, but it's only a few lines. So this is compare 0. And the first thing I'm doing is getting a line of text. But notice what I'm doing for the first time. What is different clearly about line 21? Actually, wait a minute. This is copy 2. That is not even the right program. All right, spoiler alert. All right, so never mind that. That's the answer to a future question. Here is compare 0, and I'm about to get a line of text. Program's much simpler. So this is straightforward. This is like week 1, week 2 stuff at the moment. Strings S gets getString. Now I say it again down here. String T gets getString. And then the last thing in this program, as its name suggests, is I'm going to try to compare them. So if S, the first string, equals T, then I'm going to say you type the same thing, else I'm going to say you type different things. So let's compile and run this program. So make compare 0. Looks good, no compilation errors. Let me go ahead now and type /compare 0. Let me go ahead and say something like Davin and something like Rob, and I type different things. So far, so good. Program seems to be correct. But let's run it again. Say something Gabe. Say something Gabe. All right, maybe I hit a space bar or something funky. Let's do it again. So Zamila, different things. So what is going on? So we have these 2 lines of code, getString, being called twice, and then I'm simply trying to compare S and T. But what really then is going on? Well, my handwriting's about to butcher this example somewhat, and let's actually throw this up over here as well. Okay, so we have a line like string S gets getString. So that's simply the first interesting line from that program. But what all this time has been going on underneath the hood? Well, on the left-hand side is string, which is some type of variable, and it's called S. So I know that this is using memory, or RAM in my computer somehow, so I'm going to abstractly draw that as a square. 32 bits, it turns out, but more on that in the future. And then what's going on over here? Well, getString obviously gets a string from the user, and getString got Zamila, or Gabe, or Davin. So let's choose the first of those, which was Davin. So effectively, what getString got me in that first case was D, A, V, E, N, and then what else did it give me secretly? Yeah, the \0 or null character. So it effectively gave me a string, but we already know from previous looks that a string is just an array of characters, and it's terminated by this special sentinel character \0. But if this is true, and this is a square, this is clearly a much bigger rectangle, and indeed this is, I claim, only 32 bits, and this is clearly more than 32 bits, because this is probably 8 plus 8 plus 8 plus 8 plus 8 plus 8, just because of bytes and ASCII. How the heck are we going to fit Davin into this little box here? Well, what is getString actually doing? Well, this grid here represents my computer's memory, or RAM, so let's arbitrarily say that if each of these represents a byte, then we can think of each byte as having an address, like 33 Oxford Street, or 34 Oxford Street, or 35 Oxford Street. So just like homes have addresses and buildings have addresses, so do individual bytes of memory have addresses, or numbers that uniquely identify them. Now this is arbitrary, but to keep it simple, I'm going to use hexadecimal, just by convention, but the 0x means nothing other than this is hexadecimal. And I'm going to claim that the D ends up at byte 1 in memory. I got nothing else going on in memory, so Davin got the first spot at byte 1. This then is going to be OX2. This is going to be OX3. This is going to be OX4. This is going to be OX5. This is going to be OX6. But once you start thinking about what the computer is doing underneath the hood, you can start to infer how you, some years ago, would have implemented C itself. What is getString probably returning? Because it feels like it's not returning Davin per se, because he's surely not going to fit in this little box. So what is getString probably returning? Yeah. The location of Davin. And it's been doing this ever since week 1. What getString is really returning is not a string per se. That's one of the little white lies. It's returning the address of the string in memory. The unique address. Davin lives at 33 Oxford Streets. But more succinctly, Davin lives at OX1, address number 1. So what gets put in this little box then, to be clear, is just the address of that string. So all this time, this has been going on. But what this hints at now is that if all S has is a number inside of it, who's to stop you, the programmer, from putting any number in any variable and just jumping to that chunk of memory? And indeed, we'll see that's a threat next time. But for now, this feels insufficient. If I say, get me a string, you give me Davin, but you don't really give me Davin, all you give me is Davin's address, how do I then know for sure where Davin begins and ends? And the story's getting weird. Where Davin begins and ends, and then the next string in memory starts. Well, if you're handing me the beginning of Davin, essentially, how do I know where the end of his name is? That special null character, which is all the more important now if strings underneath the hood are simply identified uniquely by their location in memory. So all this time, that's what's been going on. So when we look now at the code here, explain, if you would, the bug in line 26. Why is Zamila and Zamila different? Why is Gabe and Gabe different? Yeah, and back. Simply because they have different addresses. Because when you call getString again, which I'll do quickly here, if this is the second line, string t, as I did in that program, equals another call to getString, the next time I call getString, I'm going to get a different chunk of memory. getString is allowed to ask the operating system for more and more memory. It's not going to reuse the same 6 bytes every single time. It's going to get a new chunk of memory, which means t is going to get some other value over here. So when I do s equals t, you're not comparing d against this and a against this and v against this. You're comparing this against this, which frankly is pretty useless. Is pretty useless, because who really cares where the strings are in memory? And indeed, we haven't, and we're not going to start particularly caring, only to the extent that bugs can arise and security threats can arise will we actually start to care about this. So let's fix this problem. Turns out you can fix it super simply, and let's actually, before I reveal that again, what would you do if in a CS50 class and you had to implement a comparison against 2 strings? You clearly can't just use s equals t, but just logically, how would you compare this string against this string using C code? Yeah. Perfect. Yeah, just use a for loop or a while loop or whatever, but just apply the basic idea that if this is a chunk of memory or an array, and this is, iterate over both at the same time and just compare the letters. And you got to be a little careful because you don't want like one finger to go past the other because one string is longer than the other. So you're going to want to check for this special value at the end null, but it really is, in the end, as simple as that. And frankly, we don't need to reinvent that wheel. Here is version 2, and what I'm going to say here is that instead of comparing s equals t, I'm instead going to say if string comparison of s comma t equals 0. Now, what is string compare? Turns out it's a function that comes with C, whose purpose in life is to compare 2 strings. And stir compare, if we read its man page or documentation or CS50 reference, it will simply tell you that stir compare returns either a negative number or a positive number or 0, where 0 means they're equal. So just conjecture, what might it mean if stir compare returns negative value or positive value? Yeah, greater than or less than. So if you wanted to sort a whole bunch of strings in a dictionary, as we will eventually in the, down the road, perfect function to use potentially, because it's going to do that comparison of strings for you and tell you, does A come before B or does B come before A alphabetically? We can do exactly that. And notice I did one other thing in this example. What else has changed higher up in this main function? Char star, and this is that other white lie. All this time when you've been writing string we have been secretly rewriting string as char star so that Clang actually understands you. In other words, in CS50.h, and as we'll eventually see, we made a synonym called string that's the same thing as char star. And for now, know only that the star, in this context at least, means the address. The address of what? Well, the fact that I said char star and not int star or float star means that char star is the address of a char. So this little box here, aka string, is really of type char star, which is simply a fancy way of saying in this box will go an address. And what does that address refer to? Apparently a char. But we could absolutely have int star and other things, but for now, char star is really the most straightforward and one of interest. So this problem's going to arise, though, again. Suppose I open up this program. Let's see if now we can predict what's wrong with this code. So in this program, copy 0, I'm going to go ahead and again call getString and store the value in S. And then why am I doing this? Just as a reminder from weeks past, we did say that getString sometimes returns null. What does it mean if getString returns null? Like something went wrong. It probably means like the string is too big, the computer's out of memory. It happens super, super, super rarely, but it could happen. We want to check for it, and that's all we're doing. Because we'll see now, if you don't start checking habitually for things like null, you might actually start to go to addresses in memory that are invalid. And you're going to start inducing more and more segmentation faults, or in a Mac or a PC, just causing a computer to hang or a program to freeze, potentially. So now I claim in copy0.c that I am going to copy these strings by way of line 28. And then I'm going to claim at the bottom here that I'm going to change one of them. So notice this. I'm calling our old friend Sterling, and just explain in English what this line 34 is doing. What does t bracket 0 represent on the left? Yeah. First character of t. That's it. First character of t, I want to assign the uppercase version of the first character in t. So this is capitalizing the first letter. And then the very last thing I do in this program is I claim, here's the original, S, and here's the copy, t. But based on the story we've just told about what strings really are, what is line 28 really doing, and what is the resulting bug going to be on the screen? So first, the first question, 28. What is string t equal s really doing? If we have on the left-hand side here, string t gets s, semicolon, that gives me one box here and one box here. And suppose this address is 0x, let's say 50 this time, arbitrarily. What does string t gets s do underneath the hood? It stores the memory address there, so 0x50 goes there. So if now I go to the first character in t and uppercase it, what am I effectively doing to s? I'm really doing the same thing, right? Because if address 0x50, and just, I don't have much room on the board here, but assume that this is 0x50 down here, somewhere in my computer's memory, and I have, for instance, Gabe in lowercase here, like this, and I have said t bracket 0 gets capitalized. Well, t bracket 0 is the first letter in t, so little g is going to become big G. But the problem is, what does s also point to? The same exact thing. So simple explanation, perhaps, even if the syntax is a little weird. So let's do this. Make copy 0, and then / copy 0, say something, Gabe, and unfortunately both of them have now been capitalized. But for that underlying reason that we're simply now dealing with addresses. So how do we begin to address, no pun intended, how do we begin to address this particular problem? Well, in copy1.c, things are going to get a little more complicated, but I would claim sort of a conceptually simple solution. So hard to get at first glance, not going to be easy for the first time you type it out, perhaps. But if the problem is that simply doing t equals s just copies the address, what, again, if I can pick on you, is going to be the solution for actually copying a string? Yeah, so we're going to need a loop again, and because if we want to copy a string s into another string, we probably want to do it character by character. But the problem is, if this is originally s, now we need to start explicitly allocating memory for t. In other words, let's redraw this one last time. If this is string s gets string, and let's put this up here as well. This is get string. And then the picture for something like that is going to be, as before, GABE\0. That looks a little something like this. And S, therefore, and we call this 0x50, and that's going to be 51, 52. So this is 0x50. And then I do string t. In memory, that's just going to give me a little square like this. So what's the key step now? If I want to copy S into t, what blank do we need to fill in here? Or what do we need to do at a high level? Yeah? Someone? Yeah? Yeah, we need to like fill in this blank. I can't copy and then capitalize Gabe's name until I ask the operating system for another chunk of memory that's at least as big as the original. So that leaves us with the question, how do I ask the operating system, not just for a simple little pointer, as this is called, an address, a pointer, not for a simple little box like this called a string, how do I ask the operating system for a big chunk of memory? Thus far, I've only gotten that back indirectly by calling getString. So how is getString even getting its memory? Well, it turns out that there's this other function here that we'll now start to use. Now, this looks way more cryptic than, and I am the only one who can see it. This line looks way more cryptic than it should at first glance, but let's tease it apart. On the left-hand side, I have char star t. So in English, let's start to formulate proper sentences in technical jargon. So this is allocating a variable of type char star called t. Now, what does that really mean? Well, that means what am I going to put in this variable called t? An address of a char. So that's just a simpler, more reasonable way of describing the left-hand side. So that creates this box here only. So the right-hand side presumably is going to allocate that bigger chunk of memory. How? So let's tease this apart. It's overwhelming at first glance, but what's going on inside here? First, there's malloc, which is apparently our new friend, memory allocate. So this is the argument being passed into it. So it's a pretty big argument. So let's tease this apart. Strlen of s, of course, represents just the number of characters in S, so the length of S, the original string, so GABE. So it's probably 4 in this case. Why am I doing +1 after calling Strlen of S? For that special null character. If you ask me what's the length of Gabe's name, I am going to say 4. Underneath the hood, though, I need that 5th byte for the null character, so that's why I'm doing the +1. Now, just in case you are running this program on a computer other than, say, the CS50 appliance, where the size of a char might be different from my own computer, turns out that I can call this operator size of and just ask the computer, what is the size of a char on this computer? And by multiplying 5, in this example, by the size of a char, which on most computers will just be 1, malloc is going to allocate for me this big chunk of memory over here on the right, and it's going to return, it is a function, so it's going to return to me what? The address of what? Of the memory it allocated. So I have no idea, frankly, where this is going to end up. I'm going to propose that it's going to end up at 0x88. Completely arbitrary, but somewhere other than 0x50, because the operating system, what Windows and Mac OS do for me, is make sure that it's giving me different chunks of RAM. So this is the value where this chunk of memory might end up. So this is what ends up in here, 0x88. So now clearly I can understand that this is not the same as this, because they're pointing at different chunks of memory. So if I now actually want to copy this in, let's do your proposed solution. All right, let's just go create a for loop and do t bracket I gets s bracket I. Because now I can use this array-like notation, because even though malloc very generically allocates me memory, memory is just contiguous bytes. Byte, 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 back to back to back. I can surely, as a programmer, treat it as an array, which means I can use this, finally, familiar notation of just some square brackets. So let me pause there, because this is a lot all at once. Even though the basic idea to recap is that string all this time is not a new data type per se, it's just a so-called pointer, an address of a character, which just means it's a number that by human convention we tend to write as like 0x something. But it's just a number like 33 Oxford Street, which happens to be the CS building's address. Any questions on these details? Yeah? Why do we check for t equal to null? If we read the documentation, great question, for malloc, it's going to say in fine print, sometimes malloc might return null, just like getString. And indeed, getString returns null if in turn malloc returns null, because getString uses malloc, and that might happen if the OS, Mac OS, Windows, whatever, is simply out of memory for you. So that's what happened there. And let me reveal one other thing that might just blow your mind or completely be too far over the line. But let me pull up this same for loop for copying, which a moment ago, recall, was this. T bracket I gets S bracket I. Nice and user-friendly. Feels like week 2 again. But this version actually can be rewritten as this, which looks cryptic. It's a technique called pointer arithmetic, address arithmetic. But why does this work? Now, annoyingly, the authors of C decided to use the star symbol for different purposes. We've seen it used once already, char star, which means give me a variable that's going to contain the address of a char. So char star in that context means give me a variable. Unfortunately, if you use the star without a word in front of it, like char, it's now called the dereference operator, and we'll see more of this before long, but it just means go there. It's like saying if someone handed me on a piece of paper 33 Oxford Street, if I do star 33 Oxford Street, that means go down the road to the CS building. So star just means go there if there's no word in front of it. So what is t, to be clear? T is the address of the chunk of memory that was given back to me. S is the address of what, to be clear, in the example we've been discussing of lowercase Gabe? S is the address of Gabe's original name. So it's the address of this chunk of memory. So if I say t plus I notice is just our old friend. It's just an index variable that's iterating from 0 on up to the length of the string s. So it's going to be 0, then 1, then 2, then 3, then 4. So let's assemble these new Scratch-like puzzle pieces, if you will, even though, again, the syntax is far more arcane than Scratch. So t is an address, plus I is going to give me a number, because these are all numbers that we've been drawing as hex, but they're just numbers. So if the address of t we said was OX88, what's OX88 plus 0? Even if you don't really even if you're not comfortable with hex yet, take a guess. Still OX88. So what does star OX88 mean? It means go there, which means effectively put your finger here. And now on the right-hand side of this expression, star, and then in parens, s plus I means s, which is the address up here of the little g. S plus 0 is, of course, s, whatever s is. So now it's star s, which just like star 33 Oxford Street means go to the address s. So here's this finger, right hand. So what am I going to copy into what? The thing on the right, which is Gabe, little g here, into here. And so the effect of that first iteration of the loop as you proposed, even though it looks crazy more complicated than anything we've seen before, is simply saying go here and copy that character here. It's giving you a map to both locations. And we'll see far more of this, but for now, the hope is just to introduce some of these basic ideas. And indeed, let's look at one final program here, and then the promised claymation, which will make everything all right. All right, so let me open up. There we go. Oh. So we'll come back to this picture before long. Let me open up this final example here. So here is a super program that accomplishes nothing in life that does the following. It first declares two variables, x and y, that are not numbers this time per se. They're not integers per se. They are apparently int star. So just anyone, what does it mean if your data type, your variable, is of type int star? That's the address of an int. So I have no idea where it is yet. It just means put eventually the address of an int here, OX50, OX88, wherever it is in memory, an address is going there. And that's what y is going to be as well. If I now say x equals malloc, size of int, this is a fancy way of saying, hey, operating system, via malloc, give me enough memory for the size of an int, which is probably going to be 32 bits or 4 bytes. So what does malloc return? Malloc returns an address. So what's going to get stored in x? The address of the chunk of memory, the 4 bytes that malloc just found for me by asking the operating system. Now, meanwhile, line 4 here, the star x equals 42. Just to be clear, what's going on there? On the left-hand side, star x. That's like star 33 Oxford Street. So star x means what? Go to that address. Wherever that chunk of memory is, go to it and put what there, obviously? 42. All right, star y, same idea. Go to the address in y, put the number 13 there, but, what is y at the moment? There is no memory for y. So what does y probably contain, as we've been saying? Some garbage value. Now, garbage value is still a number. It can still be mistaken for an address. It's as though someone scribbled something down and I misinterpreted it as meaning some building down the street. And if you just try to go into some building you don't own or some chunk of memory you haven't been given, bad things might happen. Computer might crash or some other undetermined behavior might happen. So the intro then to Binky is this. I still remember 20 some odd years later, where I was when I finally understood pointers, which is to say, if you leave here in 3 minutes and think, I don't understand pointers, realize I have remembered for 20 years for some crazy reason when and why it finally sunk in, sitting with my teaching fellow, Nishat Mehta, in the back of Elliot's dining hall. And I've remembered this because this was one of the topics I, in particular, struggled with, and then it finally clicked, like I dare say a lot of topics eventually will. And now to make that feel all the happier and all the more convincing, let's take a final look in our last 3 minutes here at Binky from our friend Nick Parlanti from Stanford.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
That's it for CS50. We will see you next week.